Okay, so welcome everyone to this session of AI for Good. We had a small summer break, but we are back now. So I have the pleasure to have Guillaume Couairon, who is an AI research fellow at INRIA. So INRIA is the main, if you're not familiar, is like the Stanford or MIT for computer science in France. It's the main research institute in computer science. He got his PhD there, I believe, on while doing some research at Meta at a fair. So Meta has a big research center in Paris. He got a master's degree from Oxford and his undergraduate degree from Polytechnique. So today he's going to talk about weather forecasting, but his research goes beyond this. He has done a lot of research in diffusion models and a lot of advanced AI models, and you can check his Google Scholar page. Today, I invited him to talk about weather forecasting. So I'm far from a specialist in this field. I've noticed like a lot of large companies have introduced very interesting models. NVIDIA, Google, and some other research centers like Argonne. And so I was very happy to see that INRIA and that Guillaume also came up with very interesting models. So it's an opportunity for us to learn about what's happening in AI and weather forecasting, what was done before, what is done now, and the big improvements on solutions that they are coming up with. So I'll give you the floor, Guillaume.
Yeah, well, thank you very much for the introduction. So yeah, I'm gonna give a bit of background about myself. As you said, I've done my PhD with Meta, but it was with Sorbonne University, and it was until last year. And I did mainly work on diffusion models for image editing, so kind of like in the traditional AI framework. And since a year, I'm at INRIA. And I'm in this team called Arches at INRIA, and we try to address climate change issues and sustainability. So try to develop machine learning methods in those fields. These are the people in my current team. So yeah, I'm gonna talk a bit about AI for weather forecasting, but also some other applications that we are interested in. So I thought it would be nice to start with a project I did during my PhD. Since this is a summit on AI for good, it's another interesting application of AI to process satellite images. Then I'll talk, of course, about weather forecasting, give the context, the recent advances in AI for weather forecasting, and I will present my own work at INRIA, which is dubbed ArchesWeather. And then I'll talk a bit about future work, whether we can do generative AI for weather forecasting. And I'll talk a bit about the extension of what we do to emulate climate models and not only weather forecasting models. So yeah, that's the program. Don't hesitate to interrupt me at any time if you have some questions. I'm happy to answer them during the talk. Otherwise, we'll have some time at the end to discuss. Okay, so let's jump in with the first project that I did during my PhD. And it consists in a very simple task. We take satellite images that are RGB images, so no other information. And the aim is to predict the height of trees on the images. And so why we were interested into this task is because at Meta there was already some satellite images that have been built and that were very high quality. They were like 50 centimeters per 50 centimeters resolution, which is super high resolution, and it's very expensive to acquire. But Meta already buys these images, so we wonder whether we can bring more value to it. And there's a lot of, at this resolution, there's a lot of data around the Earth. And we were wondering whether we can leverage some of the places where we actually have some measurements for the height of the trees and try to generalize those maps to a worldwide coverage. And so the ground truth data is those tree measurements. And so usually we fly a plane over an area. And the plane is equipped with a LiDAR that sends a wave, records the answer, and then it can detect the top of the tree and detect the ground. And by subtracting, you get the height of the tree. And so we have such measurements in some areas, but not everywhere around the globe. So we have this, so the plane-based measurements, they are called dense data. And they are, at the time we did this, they were only available in the USA in sufficient quantities. But then we also have a LiDAR data that is on the ISS, and that is at much coarser resolution. So we don't have the height of individual tree, but we have like the height of trees in some area. That is 25 by 25 meters. And so the question that we had was, can we leverage both sources of data? Can we leverage the source of dense data in the US? And can we leverage this source of data that has global coverage, but at a much lower resolution? And so here is an overview of the architecture. We first start with the self-supervised training to initialize a network to better understand the structure of satellite images. I'm not going to go into too much technical detail about this. And then when this pre-training phase is performed, we do a fine-tuning on the dense data in the US, for which we have lots of high-quality data and precise data available. And then the challenge is to generalize over the globe. And for generalization, we train a network that is called a JEDI prediction that leverage the coarse data. And given an input, we both give it to the dense prediction network and to the network that predict something, but that one was trained on the coarse data. So this network generalizes better, but gives less precise estimations. And this one gives precise estimations, like precise relative heights inside the image. But the global the height of the maximum height on the image can be a bit off in the generalization. And when we combine those two networks, we actually improve generalization across the globe.
Is there a notion of weight between these two models? Know how much you should put on the coarse model versus the more granular model, or have you experimented with that?
They don't exactly provide the same kind of output. So we kind of leverage the two outputs, but without really putting a weight into account. So it's more like we use this map to tell us the correct maximum tree height on the image.
Mm-hmm.
Then we use this map more as a kind of rebalancing the difference between the relative heights in the image.
Okay.
And so the result is that we have quite precise maps, but this is also partly due to the resolution, the high resolution of the input images. And there is this method that we propose that helps to generalize outside of the US, even if we only have dense data in the US.
So this can be used for like crop monitoring or this kind of things too, or no?
Yeah, that's the hope.
Yeah.
That this can be used to monitor carbon stocks in forests. So right now it's not precise enough to monitor the growth of individual trees. But once you measure it on the whole forest, you have some averaging effects and you can measure the growth of the forest. So yeah, the hope is that it can be used to like monitor the global carbon stock. Okay, so that was an introduction on this project. Now, what I'm interested in is diffusion models for stochastic dynamical systems. Because these kind of systems, they are everywhere in science. Whenever we model some phenomena with partial differential equations, and I'm interested into two specific dynamical systems. One is atmospheric dynamics, so a very large scale system that is very useful to predict the weather. And the other one is a climate model emulation. And so in that case, the idea is more to have some simulations made by climate models. So physicians come up with climate models and law that will tell us how the climate is going to change in the future. But these models are very costly to run. And we try to make diffusion models or generative models that can emulate these climate models, but with a lower inference budget. So weather forecasting, just to give a bit of context of why this is a useful task. So first, when we talk about weather forecasting, one important task that is related to climate change is to be able to predict extreme events, such as tropical cyclones. And these cyclones and extreme events cause a lot of damage. And if we can better predict them with machine learning, we can save lives. We can deploy operational measures to reduce the economic impact of these events. So it's true for tropical cyclones, but it's also true for heat waves and cold waves. Another interesting application which drove my interest in the field is how weather forecasting can be used for the energy transition. And if you're correctly able to predict the weather, you can predict the energy demand and the energy offer. So if you predict the wind and the solar irradiation, you predict the output of windmills and solar panels. And if you can correctly predict temperature, you can predict cold waves during the winter. And in France, this is very correlated with energy demand to heat homes. And so if you are able to better predict those two sources, it's good for balancing it's good for managing the electricity grid. That is becoming an increasing challenge with more and more intermittent sources of energy, sources of electricity. And then another interesting reason to study weather forecasting is that it's very similar to climate change. So when we do climate simulations, basically what we do is a weather forecasting simulation that is based on almost exactly the same equations. But for a climate simulation, we run it at a coarse resolution to be able to run it far into the future. Whereas weather forecasting, it's run at a low resolution, and it's more for forecasting for a few days. So these are some reasons to study weather forecasting and to try to improve weather forecasting algorithms. And this is a problem that has been studied a lot for like 40, 50 years. And there was this paradigm of numerical simulations that brought great improvements, but we are now kind of reaching the limits of these improvements. So here what you see is like a performance metric over when we predict a weather variable that has been steadily increasing since the 1980s, but now we are like reaching a plateau for these metrics. And the reason is why we model as much as we can with physical laws, but there are some limits on what we can model on the globe. And every time we want to model a new phenomena, it's a lot of work. And the question is, can you learn it more efficiently with AI? And the answer is going to be yes. So yeah, so that's one reason to go for AI. We can learn directly from data and not learn from physical laws, and that can help reduce the forecasting error. The second reason why it's a good use case for AI is that we have lots of data. We have lots of Earth observations. So the ECMWF, it's the European agency, European Center for Medium Range Weather Forecasting. And they are in charge of making these global weather simulations that are then used to initialize the local weather forecasting systems. So in France, we have we do weather forecasting on the French territory, but to look at the global weather forecasting and the global dynamics, we also make use of the outputs of this agency. And these agencies, they collect a lot of observations about the Earth that can be of different kinds. We have observations that come from weather stations on the ground, but we also have instruments on ships, on planes. We have satellite observations. We have radars. We have radiosondes, which are balloons that are floating in the atmosphere and that give us some measurements inside the atmosphere. We have some free floating buoys in the ocean. So there's a lot of data. And right now, this data is feeding physical simulation models, but there could be much more that they can do.
Why does it come from this agency? Like, for instance, in the literature, they often use this data set. Is it because it's freely available? For the United Nations, the US, they don't provide the same kind of data set?
So I'm going to talk about ERA5, which is a dataset that is used to train models. The observation data, it's kind of have a weird status. There's a lot of it that is freely available. And there's also a lot of it that is not available, but not necessarily because you have to pay. It's more like the weather agency in the world, they all communicate their measurements because it's helpful for everyone to share your data. So if you're a weather agency, you can access this data, but it's a bit harder if you're doing academic research. But now there's a trend to publish the data and make it open source so that researchers can use it. And the question you asked regarding ERA5, I think people use ERA5 because it's the highest quality training set that is available. And ERA5 is produced by ECMWF. Okay, and what is the last reason why we can use AI for weather forecasting? So it's because AI can run simulation much faster than a numerical simulation. So first, when we do numerical simulation, we have to operate at a very fine space scale on the order of a few kilometers. And also we have to operate at a time step for the dynamical simulation that is quite small, a few minutes. But with AI, we can directly do a simulation with a much larger step size. So we can directly predict what's happening the next day without predicting all the intermediate steps that are going to happen during one day. And then there's also some other reasons. AI is much more optimized to run on GPU compared to simulation code that runs on CPU. And something that is going to be very interesting for us today is that it can make precise simulations on coarser grids. So we don't have to learn weather forecasting models on very costly high-resolution data. We can train models on lower resolution data and still maintain surprisingly good results. So before talking about ArchesWeather, I'm going to give a bit about the context in which this kind of model emerged. So we have seen some papers from Huawei and Google, NVIDIA, etc., that have shown very good skill in forecasting the weather based on machine learning. So the first one was Pangu-Weather. It was the first one that really got actually better than a physical model. And so it received a lot of attention from the community, and in parallel there was GraphCast that kind of does the same thing with a different architecture. So I'm going to talk a bit about what is the common methodology between all these weather forecasting models. What do they do? First, they make a data set of the historical evolution of weather variables. So weather variables, we have typically pressure, winds, wind speed, temperature, and humidity. And so this is the step where we build the Error 5 dataset that is released by Error 5, by ECMWF. And then once we have this training dataset, we train a machine learning to predict the evolution of these variables. So given the state of all the variables at time t, we predict what are those variables the next day. So the dataset is kind of a historical reconstruction of all that happens in the atmosphere. And that dataset is built with a physical model. And then the machine learning trains to kind of replicate the historical simulation.
So could that data set be wrong? Or like, I mean, do we know that it really reflects reality? Like whatever numbers and pressure, temperature there, was it really there at that time? Or because so otherwise we are modeling a model, right? It's like
yeah, that's a good question. So this is a slide on how do we create the training set. So first we choose a physical model to do the simulation. And we also give ourselves a set of observations. And so the reason why we think that we have a good reconstruction is that we have a lot of observations about the Earth. And this datashet creation, it's like an interpolation of all the observations that we have. But it's interpolated by adding some physical priors given under the form of physical laws. And so we can have a physically consistent interpolation of all the observations that we have.
and do we know like some geographical areas are more covered than others? So I would imagine that maybe North America, Europe, maybe because they have the satellites, so they care about satellites going over like over them, whereas like maybe some other areas are less covered, like Africa. Or no, it's not the case.
So now it tends to be a bit more homogeneous, but there are still a lot more weather stations in the northern hemisphere.
Okay.
But yeah, with satellite
data quality could be worse for us in the southern atmosphere, at least historically. So it could be that model forecasting could be certainly a bit worse because of that.
Yeah. It's so now the gap is quite small between the northern hemisphere and the southern hemisphere, but it used to be a bit larger.
Oh.
And so yeah, historically we have some observations. We have some quality observations since 1979. But like in the 70s and 80s, there was still a few observations, so there was a lot of gaps to fill in. So there was a lot of work that is necessary to perform with a physical model, and you're not exactly sure whether the value is correct. So you have a higher uncertainty. On the places where you have lots of measurements, the uncertainty is a bit lower.
Is it where like diffusion models could be used to recreate data or historical data or no?
That could be an interesting application. But I don't think that diffusion models can really invent new data really better than physical models. Well, at least so even if you don't have a lot of observations in an area, so here this is an example where we have a particular kind of data that is filtered, but we actually have data all over the globe. But let's imagine that in some area we have very few data. Then the output of the simulation in ERA5, it's going to correspond to the simulation of the physical model. So we are just going to learn the physical laws that we inject as prior. In places where we have lots of data, we actually have a kind of a correction factor for the physical model that accounts for the physical phenomena that are not very well taken into account. So yeah, but usually people think that ERA5 it's a good representation of the past. It's better in the recent years, like in the last 10, 20 years, compared to what it was at the beginning, because we have much more observations now and much more satellite observations now. So yeah, a few remarks on how it works. It's a process called data assimilation. And at each step, we make a simulation with a physical model, and we use the observation data. And so the resulting trajectory that we save, it's like a compromise between the output of the physical model and the observations that we have. So I think it's illustrated kind of here. We have let's say a trajectory for our model in blue, which is like a free running simulation. But then in red, we have some observations that are inconsistent with the simulation. And so the data assimilation process, what it does is that it adjusts and creates a new trajectory in orange that is both physically consistent in the sense that the trajectory could have been generated by a simulation, but we slightly adjust the simulation so that it stays close to the observations. And that's why we believe that it's reconstruction of the atmosphere that is close to observation, so it's close to reality. But in the places where we don't have observations, it should still be physically consistent. Okay, so that's the context. That's for the training set. And now I'm going to talk about the ArchesWeather, the method we design to forecast the weather and to train algorithms on these data sets. And thank you, Amin, for the for the generation. I'm going to reuse it. It looks good. Okay, do you see my new slideshow?
Yes, yeah.
Okay. So ArchesWeather, it's a weather forecasting model that is trained on ERA5 from 1979 to 2020 at 1.5 degree resolution. So it's a coarser resolution compared to GraphCast and the other machine learning models that have been developed by Google. So typically they use a 0.25 degree resolution. So 1.5 is 6 times 6 lower. So it's 36 times less data. But it's also more manageable to run on academic resources, such as resources that we have at INRIA. So the methodology is kind
But
of
if you had unlimited resources, you could do the same thing as Google and the other guys. There's nothing inherent to the model that limits it to coarser resolution, right? So it's
yeah, exactly.
Yeah. Okay.
So the methodology is we train a SWIN-U transformer to predict the 24-hour increments of physical variables. So we predict how the pressure is going to change, how the temperature is going to change over 24 hours. And The end results is a series of models that are very efficient. They are trained with low computational budget. So here it's a plot of performance metric as a function of the training budget for different models. So Keisler GNN is kind of the first model that really sparked this revolution of ML-based weather forecasting. It was trained with a budget of a few V100 days. And so we train with that order of magnitude for the computational complexity. So that's a series of model ArchesWeather for different sizes. So S is small size, medium, large, and an ensemble of models. And what we observe is that we have very good accuracy, especially for our M4 model, which is the ensemble, and it beats the Pangu-Weather model regarding this metric. So here it's the relative improvement over IFS HRES. And IFS HRES, it's a physical model that is used by ECMWF. And here we have something that is kind of magical that happens for these models, is that they actually beat the physical model. Even though a physical model is used to create the training set, because of the data assimilation process, the machine learning models that are trained, they kind of absorb some of the biases coming from the observation data, and they can have better forecast performance in the downstream tasks.
Who runs the IFS HRS ES model? All the agencies run the same models, or do you have?
No, it's only the ECMWF runs it.
Oh, okay.
It's their own model, and they run it for everyone. And sometimes they provide so they provide the outputs, but it's a lot of it's a very heavy infrastructure to run the model.
So each country just use the output of their models. They don't do their own models.
Exactly. Yeah.
Ah, okay.
Yeah. And so then the countries, they can do local weather forecasting with models that take as conditioning the global simulation made by the IFS HRES.
Okay, so this is a big deal then, right? To do better than this benchmark.
Yeah, this is a huge deal, and this is I think the start of the revolution, because the domain people, they were not expecting that.
Yeah.
Whenever they saw that machine learning models started to do better, they really got really interested in this, and they are now investing lots of resources to develop
And
this
and
kind
this
of
happened 2 years ago, or when was
this happens. So Pangu-Weather, it was the first paper was on archive 1.5 year, 1 year and a half, 1.5 years ago.
Yeah. Oh, okay, so very recent. Okay, great.
So relatively recently, yeah.
Yeah. Interesting. So it comes from China, right? It's I think like a European, North American researchers who have come up with that. Yeah.
Yeah, but they were in the race also at the same time. So I think it's more that
Okay.
Pangu-Weather, they really rushed to make the first paper out.
Yeah. Okay.
But like the two teamworks were practically at the same time. But I think what's really impressive is this model that is again a few months earlier by Keisler. And so this is a single author paper, and it really showed some good performance. And I think it's sparked some interest again, because people have been trying to do this for some time.
Yeah.
But it's really when Error 5 came out, and when we had some high quality available data, that this started to work well.
Okay. Great.
So ArchesWeather, it's based on Pangu-Weather, and the same kind of architecture, which is this wind-huge transformer architecture. And so in short, we take some atmospheric data, some surface data like temperature, pressure at the surface. We embed this into a signal tensor, and then it passes into a sequence of layers. And in the middle, we have some downsampling operation to increase the receptive field of the model. So yeah, not going to go into too much detail, because this is quite similar to the architecture of Pangu-Weather. And
What is great also is that these models are open source, right? You can go, you can download the models, or you can go GitHub or Hugging Face and yeah, at least use
yeah,
version of these models, right? You're like a student or researcher, you can, yeah.
yeah, that's great. Although you don't have the training code, and
Okay.
this only came out as a pseudocode.
Oh,
That
okay.
is very
Yeah. But I saw that I think your paper, I think someone implemented the Python code or PyTorch code, right? Like for that, right? But
yeah.
yeah, yeah, yeah.
But so that's also the aim of my work is to provide something that is a bit easier to use as an open source tool,
Yeah.
so that you can directly have the training code, the evaluation code all in one place.
Well, and to run inference of your model, do you need a big, computer? You need like, many GPUs or no?
You need one GPU,
Yeah.
but if you want to run it on CPU, it's just going to take a lot more time, but it's feasible. So inference of for 24 hours, it takes not even 1 second on the GPU. It takes
Oh,
like
okay.
point two between point 0.2 and 0.5 seconds on the
Okay.
GPU.
That's impressive. On the
So
CPU, it might take a few minutes or hours, maybe.
yeah, on the CPU, it takes like one inference, it takes 1 minute.
Oh, okay.
So it takes about 100 times more.
Yeah. 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 I mean, for
Yeah,
research, it's okay.
yeah. But I mean, for research, having access to one GPU, it's usually the case for AI
Yeah.
labs. The
Yeah.
problem is more if you need dozens or hundreds of GPUs to train,
Yeah.
it's not feasible. Here, we only need like 2 GPUs to train the model.
Yeah. Yeah.
So yeah. So what we do is that we train for 24 hours, but then we can feed the prediction inside the input of the model, and then do some autoregressive rollouts. And so in that way, we have forecasts for a few days. So usually we go
Oh,
up to
before that, can you explain a little bit about the main difference between you and your model and the Pangu model? So you're talking about these, I mean, not too much to the technical details, but about the proximity of other, like, the other points that you use these, the cross correlation.
Yeah, okay. So I wanted to tease a bit the results, but I'm going to talk about
Okay.
the actual thing that we argue in the paper, which is this factorized attention. So in Pangu-Weather, what they do is they do a transformer with a 3D local attention. And what that means is that they convert the 3D
Maybe can
atmospheric.
you explain for people who are not familiar what is attention? Maybe this.
Yeah.
Yeah.
I'm gonna explain.
Okay.
Um, so what the transformer does, so the transformer is a model that processes the data. It takes a tensor that represents the atmosphere, and so it's a 3D tensor. So there's a latitude dimension, there's longitude, and then there's a altitude in the vertical dimension. So there's like this 3D block of physical variables that is processed by the transformer. And these attention layers, they help to communicate information inside this tensor. So given some physical variables at one location, what the attention does is that it looks around at the neighboring data, kind of like a convolution. And then it aggregates all of this data together to update the physical variables at the initial location. So it's an attention mechanism instead of a convolution, but it's a local attention. So it works kind of the same in that it helps to update the variables at one location based on the values of the neighbors. But what we show in the paper is that actually this is very costly to do it in three-dimensional. Because everywhere in the atmospheric tensor, you have to look for the neighbors. And this is how to propagate information from one part of the tensor to another part of the tensor when they are far away, especially in the vertical dimension. So if we want to exchange information between the lower layers of the atmosphere and the upper layer of the atmosphere, we have to do lots of propagation of information through the attention windows. And we found that to be too slow and to be a bottleneck in performance. And so what we propose is a factorized scheme where we have two-dimensional attention windows. So this is more classical. We only exchange information across the latitude and longitude dimensions. But then we allow for a much faster interaction across the vertical dimension. So it's like we connect all the layers of the atmosphere, and at a single location, a single latitude longitude location, all layers of the atmosphere are able to communicate together. And so that helps to propagate information much faster between the different parts of the tensor. Yeah, and that actually gives us some improvements, which are illustrated in this table. So what are we looking at here? We have ArchesWeather S, which is a small model, which is about 50 million parameters. It has 16 layers. Here are some performance metrics. So geopotential 500. This has to be minimized. It's RMSE error. And this is the temperature, the surface temperature. So let's look at the DED 500, for instance. With this cross-attention layer, we have a score of 50. And without it, we have a 10% worse score of 55. So it helps to improve this metric a lot, to use this cross-layer attention. And to show that it's actually a big gain between 50 and 55, we train a model, ArchesWeather M, where we double the number of parameters. And if we don't use a cross-layer attention, we have a 51.8 compared to a 50.6. So it's better to use cross-layer attention compared to doubling the number of parameters inside the model. So it shows that it's actually efficient. It helps to reduce a lot the size of the network and still have better performance. One thing that was also interesting in this study was that, as I mentioned, data is a lot more, there's a lot more data in the recent years, from 2000 to 2010. And so before that, machine learning models, they were training on the full ERO5 data set. I mean, not the full, but from 1979 till 1920. But from 1979 to 2000, we actually have less satellite observation. And so the data is a difference between these earlier years and the recent years. So there's kind of a distribution shift. And we argue that it's better to fine-tune on the recent period, and that gives us better performance, better weather forecasting performance. So yeah.
Does the gain come from that, or I mean, maybe you do some ablation studies and you
Yeah, so there's an ablation study here where there's without fine-tuning and the version with fine-tuning.
Yeah, okay.
And so the gain is much smaller than the CLA, but it's still quite significant for some variables like DED 500.
Okay.
Yeah, so the main conclusion is that weather forecasting is accessible to academic labs, and also that ML-based weather forecasting is skillful even at 1.5 degree. So here I was comparing some of the original models like Pangu-Weather with ArchesWeather. And actually, we have better performance as Pangu-Weather, even though the prediction is made at a much lower resolution. So 1.5 instead of 0.25. And this is true at 24 hours, but this is also true for multiple time steps.
But I saw that in their paper, they said they can follow hurricane or this kind of things. You know, that happens a lot in Asia. You cannot do the same, right, with this kind of resolution?
Yeah, so that's one of the problems. It's much harder at 1.5 degree.
Yeah.
But the reason why we do global simulations is more to have an idea of the global atmospheric movements,
Yeah, yeah,
global atmospheric dynamics. And so potentially we could still retain some of the applications like cyclone tracking
yeah.
by having some super resolution models that give you a detailed resolution over a 1.5 degree model.
Mhm.
So yeah. And so now I'm doing the diffusion modeling parts. So I'm not going to go into too much detail, but I'm using flow matching, which is a version of diffusion models. And it allows to do some sampling for the diffusion model quite efficiently. So just showing some of the simulations that we have for this model.
So for diffusion models, for people who are, I mean, you're probably more familiar with like image generation, video generation, and so on. So they all use like diffusion models, right? There's we do like
Yes.
text to video, text to image. It's all like diffusion models.
Yeah, so diffusion models, they are generative models, which means that they can generate data. So when we do weather forecasting, we can generate a prediction for the next day. But what we have is not a physically consistent state. It's more like a statistically optimal prediction. So it has very low error, but sometimes it's going to be smooth. And so it's not going to be useful when you give that to meteorologists. So the question that people had was, can you actually have an emulator of the weather, something that produces physical states? So for instance, if you want to track a cyclone, but you're not sure where the cyclone is going to go, you're going to predict a cyclone that is very smooth and that has wind speeds that are much lower. If you go to generative modeling, you can predict the full distribution, which means that you can actually sample different paths for the cyclone. And so you're gonna you're gonna recover the maximum speed for the cyclone much better. So yeah, so here we have temperature, wind speeds. This is humidity, and this is geopotential. Yeah, just showing that. Yes, these variables. So
So this is useful for insurers, for insurance company, right? For reinsurance company, they want to look at trajectory of like hurricanes, cyclones, or and so on. So
yeah, potentially they can.
or scenario analysis, to have realistic scenario analysis, right? For the
Yeah. So potentially they can call their clients to
increase the premium or the clients to move.
no, to tell them to get to a safe place.
Yes, yeah. Move
This
to
is also a government mission. But yeah. Okay, I'm gonna maybe skip this part. This is just to say that when we do forecasting with a generative model like diffusion models, we can actually sample many different weather trajectories. So we can sample what's going to happen in the future. So we don't know what's going to happen exactly, but we can say, oh, here are some possible representative scenarios of what is going to happen. And this is something that we can do with diffusion models, which is very interesting. Okay, so now to maybe quickly conclude, one of the motivations for implementing diffusion models is that we're going to be able to do some data assimilation. And data assimilation is this process I was talking about before, which is to make some predictions with a model. So before a physical model, but now it can be a machine learning model. But to adjust the predictions with all the observations that we gather around the globe. And the nice thing with diffusion models is that we have some ready-made tools to do this data assimilation process. And so one of the paper is exploring this generative data assimilation of sparse weather station observations at kilometer scales. And I think we're going to see more of those, which is a natural question when we have more and more observations data that comes inside our forecasting systems. How can we make the best out of this data? So yeah. And finally, there is a connection with climate model emulation. And here the spirit is a bit different. So in weather forecasting, we kind of want to learn the physical laws, and then we can extrapolate to do weather forecasting. But in climate models, we cannot train on past data and expect the model to actually recover climate change in the future. Because climate change in the future, it's driven by a physical process that we model, but it's not in the past data. It's we see the global warming in the future data that is performed by the climate simulations that are coming out of the climate simulations. So here our strategy is more to use some of the climate simulations that have been performed by research groups. They have done the climate simulations, they have saved the data. And the research question we ask is, can we emulate these models? Can we generate more simulations cheaply with diffusion models? Can we change a bit some of the hypotheses, like how much CO2 we emit, etc. So yes, that's it. Something that also I wanted to bring up are a few items for discussion, which is weather forecasting has been studied a lot, and we can do weather forecasting with AI, but how much of this is really AI for good? And so there are some principal reasons why we think it's going to be helpful to tackle climate change, but there can also be some reasons to doubt about it. So one of the interesting points is that we can, with AI, we can reduce the carbon footprint of weather forecasting. So right now, weather forecasting, it's made on very large CPU clusters that takes up a lot of electricity. And if you replace that with machine learning models, the efficiency gain, the energy gain is like on the order of thousands. So it's really huge. But this gain is only going to be effective if we actually don't run numerical simulations on the CPU, if we stop doing that. And the question is, are we really going to stop running the numerical simulations? And I think one of the probable futures is that we're just going to reallocate the CPUs to create the machine learning datasets or to do other kinds of simulations.
I mean, if you learn your models in France, like you have a lot of like nuclear electricity, right? So the carbon footprint should be small,
Yeah, but here the debate is it's more like this is additional carbon footprint. It helps to reduce the carbon footprint
Okay.
if there is an activity that was taking a lot of electricity that you actually reduce.
Okay.
And that's the question. Are we going to actually reduce the total electricity that is being used? Yeah. So this is a question. It's not really clear to me what's going to happen. Yeah. So
But
answer
I think anything you do that increase knowledge, on this forecasting climate change is good, I think so.
Yeah. So I think that's why we have to differentiate between some of the good reasons to do ML-based weather forecasting and climate simulations.
Yeah.
So, but then for studying climate change, we have to be careful about our messages. So what really helps to understand the processes that drive climate change, it's more climate research. But what we can bring with AI models are some statistical tools to help do the simulation faster, to do more kinds of simulations, to change a bit some conditions, to do some kind of intervention. If we change the scenario of emission, how is it going to change the global warming, etc. So it can be useful in that context. But it's still unclear what is the knowledge that is going to come out of these systems.
Mhm. I thinking, for instance, when you read about think about the weather, people always mention El Nino, El Niña, or these kind of things, Gulf Stream, changing, but that it doesn't really appear in these models, right? Can you test this hypothesis? Is it is the weather changing here because the flow in the oceans of warm water and so on is changing, or it's difficult to do that?
Yeah, that's a good question. I don't really know about whether these models have been useful to improve meteorological knowledge.
Mhm.
I think right now we're still at the stage where we test that these models actually do weather forecasting according to some physical principles.
Yeah.
So yeah, people have tried to initialize these machine learning models with out of distribution cyclones, for instance, and check that the cyclone propagates according to some prior physical knowledge about cyclones. But yeah, it's yet to be demonstrated how this can bring new knowledge to the meteorological community.
Okay. We just have a few minutes left, so let's open it to questions from the participants. Elliot, I know that you're very interested in this topic. Do you have any questions for Guillaume? Or anyone else? Raise your hand and we'll give you the floor.
Okay, so I got unmuted.
Yes, go ahead.
Yeah, thank you. So that was quite interesting, and I don't know as much as a speaker, obviously, but from a finance perspective, we have been trading with, in fact, I was interested before in insurance derivatives because of my interest in insurance and risk for agriculture and so forth. And in finance lately, we have been trading weather derivatives. Did anyone in the group look at this problem and see whether the models, beautiful models you are producing, exhibit any consistency with whatever numbers are produced on the exchange called the CBOE, where the weather derivatives are traded?
Sorry, is that a question for me?
Yes. Guillaume, you are a speaker.
So I don't know anything about the weather derivatives. What are those?
Basically, it's an instrument.
Okay.
Let's say I am a farmer, and if it's very hot in August, just before the harvest, my harvest is going to be destroyed. So I find somebody, you, mean anyone, and this somebody pays me on August 31st some amount, let's say $100,000, multiplied by max of 0 and temperature on August 31st minus, let's say, 28 degrees Celsius. So if it is very warm, this quantity will be positive and will be a way of making up for my loss as a farmer and help me keep my employees and everybody on the farm. So,
Okay.
so
So
I
it's
will.
of insurance. That's
Yes,
the temperature. If the temperature rises above some level, I'm gonna get.
exactly. Yes.
Okay.
Yeah. And so this came out first when electricity became deregulated in the world, like first in the US in 1999, then in France in 2005, and so forth. And they continue to be popular. And it's not so easy to price because there are two things. I'm not going to keep the floor too long. What your expertise is, and also what is a kind of market price of risk, the market price of temperature risk, the market price of insurance risk, if you will. But already one thing is what you are doing. It's part of the solution. And I was wondering whether someone in your team decided to look at some consistency between your model. I mean, obviously, if you do a good prediction, you can sell these instruments. You have a good idea of the temperature on August 31st when you are on May 10th, right?
I think it's a
Yeah.
good. I think Guillaume obviously hasn't looked at it, but I think it's could be a good interesting topic of research, because it's you see how market participants or businesses look at the risk and you compare with your own prediction. So you might not necessarily conclude that the businesses are wrong, but because that's that notion of market price of risk, of how averse they are to the event, right? How much they're willing to pay to hedge against that. But comparing, what would be interesting, maybe for one of your students or someone it could be like an interesting project to do. But I'm not familiar. But so you can on this weather derivatives have been around for a while, so it'd be so interesting to see what they're using today, what kind of models they're using for weather forecasting, right? And
Yeah, I just want to mention, Guillaume, for your own sake, that there is a gigantic hedge fund based in Chicago called Citadel, which used to be primarily trading stocks and bonds and all kinds of stuff. And they moved to electricity derivatives, and weather derivatives are very close to electricity derivatives for obvious reasons, right? So in any case, you may look at
it's also
that.
good. It's also strong. I mean, because many of us are based in New York, so a lot of us work in finance. But in fact, there's a big connection with finance, right? A lot of PDEs and so on. What is related to weather? Even if you go back so not necessarily to finance, but I think weather was a big interest of John von Neumann in the 1950s. Right? So one of the first computers, the ENIAC and so on, was developed. One of the projects he wanted to do was to do weather forecasting. Right? So sometimes he was interested in AI too. I think he was in computing in AI. So so somehow we are going back to the source. But there's a lot of connection between physics, computer science, AI, and so on. Anyone has a last questions for Guillaume? I mean, you can always reach out to him. He has an email. He has a Google page. But any last questions for Guillaume before we end this talk? And yeah, so Katie had the questions, but I don't know if she still wants to talk. Yes, go ahead.
Yeah, so my question is, and I'm a longtime member of the media in the US, and we focus a lot on weather forecasting in television and online and everything. So I guess how far away are these models from being able to replace what is currently being used in like the general scope of the media for mass audiences?
So these models, they operate pretty early in the chain. So before you get your actually weather forecast in the television, there's a lot of processing that is done. So these are kind of the foundational models, but once you have a prediction with these models, there are some post-processing models. Then there are some human correction by meteorologists who have experience with these models and they know a bit more about their biases. And they produce the maps, and then you have some additional processing to do the weather forecasting. So then there's of course the question of whether the machine learning models are going to replace the physical simulation models. And I'm not sure this is going to happen soon because with the physical simulation models, we have some guarantees that these models work according to physical principles, which we don't really have for the machine learning models. So there's still the question of trust. How much trust can you put into the machine learning system? And so for the ML base to replace the physical base, we have to wait until we have sufficient trust in this kind of models. But probably this is going to change with some of the startups that will do ML only based weather forecasting, and they will show very good performance. So yeah. So to answer your question, I'm not sure about the media. For the operational deployment of the machine learning models, I think it will be a few years, maybe 5 to 10 years. But
5
we
to 10
probably
years.
will still have some hybrid models, hybrid machine learning and physical simulation models. This is the most likely.
Yeah.
Okay, excellent. Okay, so thank you very much. We've been running a bit over time. It's a very interesting topic, so I encourage you to visit Guillaume's webpage, and I think like every month you have like new models coming out, and many of these things are open source. So you have a power computer, you can run these models. That is the inference stage, and it's a very interesting topic to study and to read about. So thank you very much, Guillaume. Keep in touch,
Thank
and
you.
next month we'll have something on biomedical science, and I'll give you more details later. Okay, so everyone have a great day, and see you soon.
Thank you.
Thank you for the invitation.
Thank you. Bye-bye.